Hello and welcome back to Calculus 1 section 4.5 on optimization problems.
Epstein didn't kill himself.
I know, I read on one of the exams. It was communicated at the bottom of one of the exams. So, anyway. We are interested in minimum and maximum in the setup of application problems, the ones we can make money with. So we want to take a look at a couple of problems and the procedures in which we are going to find the minimum and maximum and what we call optimize the situation. You might look for maximum profit, minimum cost, but you can also look for maximum volume or minimum surface area, or a whole bunch of application and different types of problems that you can have to utilize this process. Now, before we do any of those, let's just set up the basic idea and how all of the problems are solved. They're all solved the same way. You will have two equations combining into one equation, hitting it with a derivative, and then technically you're done. But let's say that the problems, this is going to be, again, math abstract problem, is just find x and y, find values of x and y such that the sum is, let's say, 20 and product is max. So your job is to find two values, value x and the value y, for which the x and y add to 20 and their product is maximum. So we are going to have two functions here, two equations, one for the first piece of data, and that data says that the sum has to be 20, so x plus y equals 20. And then the second one is that the product is max, where you would say x times y equals a max. So our objective is to have a maximum product under constraint that the numbers add to 20. This is a very, blah example, but it actually works very easy to understand the concept. So what you do is you take your constraint function and you solve it for one of the two variables. Say y equals 20 minus x. And then you plug that in the objective function, and you will get x times 20 minus x equals a max. And then you have 20x minus x squared equals a max. So you see now that your equation, I was about to say vacation. You now see that your equation contains only a variable x, and you are supposed to get a maximum there, right? So this is where you differentiate. When you combine two equations and you eliminated one of the variables, you differentiate in respect to the variable you have, in this case is x. And then we have the derivative of 20x is 20. And then minus the derivative of x squared is 2x. And what is the derivative of a maximum? Well, maximum is some number, right? Because all of this equals some maximum. And that maximum is a number, so derivative of x is always 0. So in 4.1, you memorized to find min and max we set the first derivative equal to 0. That's what you memorized in 4.1. Now, in 4.5 with the word problems, you actually have the word max over there, or a min, and you understand that that's some number, because x times y, which are some numbers, will give you some number when they multiply. And when you take the derivative of that max, you get 0. So all of that stuff that we learned earlier is still preserved. You still get derivative equal to 0 to find your min and max, except this is more natural way, rather than memorizing, or even talking about horizontal tangency, slope is 0, blah, blah, blah. So from here, we calculate that x is equal to 10, and then y is equal to 20 minus 10 equals also 10, and we now know that x equals y equals 10 is our solution. Boom. Now let's say you're skeptical, and you would like to do some basic calculations to kind of show that this might make sense. All right, so let's go and figure out x and y values so that they add to 20. Well, you can pick 0 and 20, and the product 0 times 20 is 0. Then 1 and 19 also add to 20. 1 times 19 is 19. 2 times 18 is, 2 plus 18 is 20. 2 times 18 is 36. So as you can see, right, it's getting better. So 3 and 17 is 3 times 17, which is very good. All right. So now you have 4 times 16 for the next one. That is equal to, perfect, 5 times 15.
75.
Yes. So as you can see, right, the product is constantly rising, right? As these numbers over here, they always add. Each pair that I have on the chart always adds to 20, because that's our constraint. Constraint says that x and y must add to 20. So here they are. So now 6 times 14. That's
84.
84. 7 times 13.
Wait, no, it's not. 91. Right?
91. Now we have 8 times 12.
96.
And then 9 times 11.
No, 99.
So it's still rising. And then we hit 10 times 10. 100. Now, the next digits are going to be 11 and 9. Well, that's 11 times 9 is going to start dropping 99. 12 times 8 is going to start dropping again, so 96, and going on. So we see that we reached the peak, right? The max product was when we had 10 equals 10, which gave us 100, and all other combinations of numbers we had with digits over here, right, with numbers, gave us smaller product. So we actually have a calculus way to determine this now, rather than computing everything by hand. So let's take a look at optimization problems that are applied, and we always start with farmer problems. Farmer problem. So what's happening with these farmer problems, these are kind of standard problems to work with. Farmer has some amount of fence, and he wants to fence off rectangular area. Find the dimensions x and y so that area is the max, right? So let's say farmer has 2,000 yard of fence, and he wants to fence off a rectangular area of maximum size. Find the dimensions. We can all imagine this. It's not that difficult. You have fence, you know what the fence is, you know where the fence goes, you know what the rectangle is, and you also have the concept of we are talking about maximum area, because when you have fence, right, you can put 2,000 yard of fence around this classroom. You just go a couple of times, right? It's okay. So the idea is to calculate what is the maximum area that can be enclosed with 2,000 yard of fence. So we start the problem with the picture, which is just a rectangle, and we have our x and our y. Now we also know that the top and the bottom are also x and a y, right? We understand that the fence goes around the perimeter, right? It's also called a perimeter fence. So we have all of those, and now we are ready to translate English into math. What are the two equations that I'm looking for to solve this problem? Perimeter and area, very good. I have given 2,000 yard of fence which goes around the perimeter, so what's the perimeter formula for a rectangle? 2x plus 2y equals 2,000. Very good. And what is my area formula, which is objective?
X times y
Equals
area.
Max. Because we want the maximum area. Good. So the top equation is called the constraint. We'll stop writing this. And then the bottom one is called the objective. Your objective is to maximize area. That's what you want, right? You want the maximum area to enclose as much space as possible to have your cattle or to plant cabbage or whatever it is, right? So we are going to divide the top equation by 2, get x plus y equals 1,000. Right, divide by 2 to make it easier, and then solve for, again, y, which is 1,000 minus x. I hope you see that this problem is exactly the same as the previous one. There's no difference. Your x times, right, so now you plug in. Your x times 1,000 minus x equals to the max. That's 1,000x minus 2x equals a max. And now we have to take the derivative. So when I take the derivative, we have 1,000.
Wait, shouldn't that?
This is over here x squared. Please pay attention to notify me sooner of silly things I write. Thank you. X times x is x squared, and now when we take the derivative, it's 2x, and we set the derivative of a maximum, which is some area, say 5,000 square miles, is going to be 0. From here, we quickly conclude that x is equal to 500 yard. And you can compute y, in this case, 1,000 minus 500, also 500, and we get that the dimensions that we are looking for is a square, very good, of 500 by 500 yard. Then you go, wait a minute, didn't we have 10 by 10 earlier? Yeah, that's what's so special about the square. Square is a special rectangle, right? That's what it is. Because what's so special about a square? Well, these two features. One is that square is a special rectangle because all sides are the same length. And the second special feature that you didn't know up to right now is that it has a maximum possible area. But
Whoa, relax, dude. Chill. Whoa. Whoa.
yeah, see that? Now, are all answers going to be x equals y equals a number?
Okay.
And the answer is hell no. Very good. So now we are going to do another farmer problem, but this time around he is going to be adjacent to a river. Now this is clearly a river because it's blue. To make this even more appealing, we'll put some salmon in it. There you go. Now you have some salmon floating about. No, they're not carrots. Carrots look like this.
Wasn't on the green. Oh, I knew it.
That's the carrot. That's the salmon. That's the carrot. Learn the difference. What, the birth defect? Oh. Has a green fin. All right.
Did you just assume his species?
I have, because it's orange. Give me another orange species.
Nemo.
Goldfish.
Garfield.
Orange.
Garfield.
Garfield. Okay, you win.
You gotta pull
So now, farmer is going to run his 2,000 yard of fence in this configuration. He is not going to fence off the side towards the river, because when you put the animals in there, they're smarter than people. They're not going to go into the river. All right? So you don't need a fence on that side. So what are the dimensions now? Excellent. So now our constraint function is x plus 2y equals to 2,000. And we're still looking for maximum. We're still looking for maximum area. So we have our equations. Now, this time around, I am going to solve for x rather than y, because I don't want to deal with fractions, right? If I solve for y, I'll have x over 2. And then I have to drag that through my calculations. So I'm going to solve for x this time. And that's going to be 2,000 minus 2y. And I'm going to plug that in this equation to have 2,000 minus 2y times y equals a max. And then 2,000 y minus 2y squared equals a max. And now, when we have one equation with one variable, we hit that with the derivative, this time d dy, because we are now maximizing y, which in terms will give us maximum x as we go back. So what's my derivative of 2,000y? Very good. Minus 4y equals 2. And we get y equal 500. Again, do not despair. X equals 2,000 minus 2y, which is 500. So there we go. So the new dimensions are 1,000 by 500 yard. Those are the new dimensions for the farm. Cool? All right. Now farmer has more land and another set of 2,000 fence. So let's see what's going to come up with the next one. Needs, yeah, it looks like it's a fence company, not a farm, but that's okay. So far, 4,000 yard of fence went into fencing the areas, right? But now, we are still going to have 2,000 yard of fence, but now he wants to have 3 separate areas here. We'll put the cabbage, rabbits, and tigers. There we go. Can't put them in the same division, right? Right? Rabbits are gonna eat the cabbage, and the tigers are gonna, rip the, right? No, you can't mix those two either. Tigers are gonna pee all over the cabbage. So.
Oh, that's the worst.
So there we go. We have these. So all right. So now we have 3 areas. We're going to call this one X and this one Y. So what is my constraint now? That's it. 2X plus 4Y equals 2,000. And we still have our XY to be max to get the maximum area. So geometrical configuration will tell us what the constraint function is. We know we're looking for maximum area, right? All right, now, I like when I don't even have to talk. It's just I just put it there and just move on. Okay. The next farmer's problem that you can also work at home because you care is if you, let's say, right, have a little area fenced off like that.
2.5y plus 2.5x is 2 down.
Exactly. 2.5y plus 2.5x is equal to 2,000. xy equal max. And then, there we go.
Is that a Nike swish?
Yeah, just do it at home.
Oh, I got you.
All right. So, these are cool problems. We do have a branch of engineering here at RV that is feeding directly into Rutgers packaging engineering because apparently it's a booming field. And packaging engineering is concerned with a lot of boxes, optimization, and a whole bunch of other stuff. Is not just boxes. We are going to work on a box now, but we don't produce anything in this country anymore, right? So we gotta ship stuff, right, from everywhere else. So let's see. You want to minimize the surface area of the box, and you want to maximize the volume of the box. Clearly, you want to maximize the volume because you can put more stuff inside. Why would you want to minimize surface area of the box? Less material, less cost. If you are able to shave off 5 cents per box, ooh. Why is the 5 cents so important? You don't even pick up 5 cents as you're walking down the street. Yeah, multiply that by 1 million boxes, right? All of a sudden it adds up to a considerable amount of money. Companies are not obsessed. Companies are possessed by, right, the idea of minimizing the cost. There's a difference between the two. Because they need to make sure that they are having the least possible cost of operation, right? So they can have as much profit, so they can have better research and development to be competitive on the market. So let's take a look at the problem which is asking us to do either of the two. I don't really care. Maximum volume of the box. Minimum surface area of the box. So which one do you want? Do you want the problem with the area, or do you want the problem with the volume?
Yes.
Volume, yeah, probably the volume. Maximum volume. Suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 108. What dimensions and volume of a square-based box? Square-based box is because this is Calc1. Any box, Calc3, because you would have three variables, x, y, and z, for three different dimensions. Now, we are going to say x and y dimensions are the same, so technically you just have then rename z to y, and you're just going to have two. So if I have a square base, it takes the same dimension, and then the height of the box, which we usually call z, we're just going to call now y, and we'll still have x and y two-dimensional problem, right? Now, those of you going to Calc 3, you will upgrade this problem into something called Lagrange multipliers, and you are going to use that technique to calculate 3D cases of this, which is even more, right, profitable going down the line. So now what I'm going to do is draw this square x and x, and then we're going to add some height to it. Which will be y. So this is your, now this is a luggage obviously, so we're going to have a handle on top. There you go, perfect. So now, you can put wheels on the bottom too. They said that length plus the width plus the height cannot exceed 108. Length plus the width plus the height cannot exceed 108. Okay, so we'll set it at 108 because that is the largest we can have. And they are looking for the maximum volume. What's the volume over here? X times x times y, which is x squared y, and that needs to be a max. Awesome. So I have 2x plus y equals to 108, and x squared y equals to a max. So we solve the top equation for y, which is 108 minus 2x, and then we plug that into this one, so that's x squared times 108 minus 2x equals a max, and then we hit, well, no, we first distribute. So 108x squared minus 2x cubed equals a max. And now that we have this model, we hit this with the x derivative, and now we are ready. So 108 times 2 is, very good, minus 6 squared equals 0. Now, 216 is divisible by 3, and it's even, which means it's divisible by 6, so we can factor out 6x. 6 into 1 goes 3. Thank you, Komr. Minus x equals 0. When we solve the first equation, we get x equals 0. what do I do with this information? Throw it in the garbage, exactly. Why do I throw this answer in the garbage? Yeah, because the length of your suitcase cannot be 0. Yeah, well, I have actually one right here, as you can not see it. And then we have 36 minus x equals 0, x equals 36 inches. That's the length and the width of the box. Now we also have that y was equal to 108 minus 2x, which is 108 minus 72, which is, oh, aren't we surprised, 36 by 36 by 36 inches for the box. You bring the cube, right? You bring the cube, and you are guaranteed, for whatever restriction you have, it's going to be maximum volume inside. As your packaging engineering, old spark. Nice. Okay, let's see what else cool we can get. Ooh! Let's do the pool problem.
The whole time we're trying to tread water while solving that.
Yes. You are only allowed to exit
if you
solve it. Yeah.
No paper, no calculator, just treading. Oh.
Here is the problem, guys. You know the surface area of the pool you want to have. So let's say the pool, which just disappeared, so let's say you want to have 8,000 feet squared of water, right? For swimming, splashing, and what else? Now, you also want to have a walkway made out of concrete, right? So kids can run and then scrape their knees when they fall. I thought that was the sole purpose of the concrete around the pool, because they clearly say do not run. They're the only ones who run and fall. So anyway, so you want to have this thing, and let's say, oh, some painful memories I see coming back. Okay, some of you are like, oh, I remember that thing. Listen to older, okay? So we want this one over here to be at least 10 feet, right? So you can have those chairs and still walk around. So on these sides, you want maybe 10 feet. And on these sides, what are we going to put here? 1,300 feet. You're disqualified from it. We'll put 8 feet here and 8 feet over here. Now, you're already paying the flat price for the pool of this size, so don't worry about that. We are worrying about the concrete, right? Because our goal is to minimize the amount of concrete, which minimizes the cost for the concrete, obviously, which minimizes the cost of the entire build. So you're paying for 8,000 square foot pool no matter what, right? That's it. Now, the only thing that you have to build in addition is this extra, right, concrete surrounding around the pool, and we want to minimize the cost. So basically, by minimizing total surface area, and being that the cost of the pool is fixed, you are technically minimizing the amount of concrete that you are pouring around the pool. So the shape of the pool will arrange itself in the best configuration, so you have minimum surface area for the concrete, which means minimum cost for the concrete, which means minimum cost for the entire project, being that the pool has a fixed price. Now replay this back, because I said it real quick. All right, so, yes. We will see. I hope so. But let's see. So I'm looking for minimum surface area, and I am looking for dimensions x and y, which are dimensions of the pool. And we will find how awful that thing is. At least you can swim in circles like this, right? Actually, that would not be good, because you never know who had a heart attack and still trying to swim their way out. Yeah. Anyway.
Just float.
All right. So, what are my equations? Equals 8,000. Excellent. You immediately see the area of the pool. So xy equals 8,000 is your constraint, because you are set to have 8,000 feet square pool. Right? What's your objective function? What are you minimizing? The total area, right? So what are the dimensions of the total? What happened?
Y plus 10, x plus 8
What?
y plus 8 y.
Y plus 10 times. Oh, yeah, very interesting.
X plus 20.
In parentheses.
X plus, thank you, Madam President, x plus 20,
Plus the times y plus 16.
y plus 16 equals minimum, right? We are looking for the minimum, and that's our objective. Total area, total area is when you multiply the length, and the total length there is x in the middle. So that's x, and then you have, so x over here, and then you have a 10 over here and 10 over here, right? So that's 10 plus 10 is 20, and then plus x, and that gives us x plus 20 for the length. And then you do the same thing on the side, where you have y in the middle, and then 8 and 8. 8 plus 8 is 16 and a y. So now we understand how we got to the equation. And all we need to do now is to compute that, and we're done. So we can solve the top equation, let's say y equals 8,000 over x, and then plug that into this equation, which is x plus 20 is equal, times 8,000 over x plus 16 equals to minimum. Before you multiply, FOIL this, right? Multiply it out, because why use product rule if you can just do the algebra? It's easier. So x times 8,000 over x is just 8,000. X times 16 is plus 16x. Plus, this is 16,000 over x plus 320 equals a minimum. And now you can take the, I know I can add the constants, but I don't want to waste a step, because what happens with 8,000 and 320 when we differentiate? You'll get 0 for both of them. So, oh yes, 160,000. Yeah, it's just 10 times off. Like, what am I going to lose on a test? Like -2 for error? Oh, it's a big deal. Let me tell you, you will never work again, okay? It's as simple as that. As soon as you are done with your education, these types of mistakes, make sure you die, all right?
That is unfortunate. Let me say.
All right. Make the error 10 times, not a big deal. It's like what? Oh, your quote was $30,000 for the whole pool? And now it's 300,000. Like, don't worry about it. Yeah, a little bit overhead. This is not it's a standard contractor thing. All right. So that's a 10 times, right? Just an extra zero. Who cares? -2 on a test. All right. So derivative of 8,000 is 0. Derivative of 16x is 16. And then we have minus 160,000 over x squared equals 0. And I'll need abacus for some of these calculations later. I don't want to think. And then we have 160,000 divided by x squared equals to 16. Then move this x squared with the 16. So now divide by 16, you get 100,000 equals x squared. And this is the odd number of zeros, so it's not going to be nice square root. So we have square root of 100. That's what I'm thinking. It's 10,000. So it is a nice square root, which is 100. Yeah. No, it's okay. All right. So 100 feet. And now we can calculate our y, which was 8,000 divided by 100, knocks off zeros, is 80. So the dimensions of the pool are 100 by 80 feet. And that will guarantee the minimum surface area of the entire pool, because right, we are minimizing the area, and then the pool in the middle is the fixed size of 8,000 square feet. And there you have the dimensions, right? So now you go and you build this thing. Another application for this would be the textbooks or the books, right? Because once you know the content of the book, you can start playing with optimization and margins. And you want to minimize, again, why do you want to minimize the page size? Because it's insanely expensive to make books, right? You have to print. If your calculus book has what, about 1,300 pages, cut that in half, right? Take 650 papers that are printed both sides. So printing 650 papers on both sides, can you imagine if those were, legal size? So at that point, you might as well make a scroll. We should actually have a book on a scroll. That would be so awesome, right? Can you imagine? I just have like
line number 3042.
Right, real tears.
I think I found it. Oh, I missed it.
Anyway,
Just scroll back up.
scroll up. Nice. Okay, so that's good. So the same problem, right? You just say, okay, I want the 1.5 inch margin on this side, and maybe 1/2 inch top and 1/2 inch bottom, and then 1 inch on the right, whatever, right? You get the idea. It's the same calculation. It's just going to be, instead of feet, it's going to be in inches or centimeters, right? For the rest of the world. And For all of those who don't play baseball, how about that? So you can do 1.5 or centimeters for all of those who don't play baseball. And that's it. Let's take a look at something else. Now, again, you can be contracted to do the calculation for this. Maybe you work for a company that is, working with this concrete patty around the pool and so on, or just a freelancer that they always call when these calculations need to be done. Oh, they have a similar problem, but it's optimal garden. They have a flower garden with the grass around it. Like, no one cares. Really? What else could we? All right, let's take in consideration one of the cost problems where we actually are going to calculate the cost. Oil rig problem? Whatever. What do I have? I have a shore and a sea on this side, and I'm going to have an oil rig drilling and polluting at the same time.
Sounds about right.
So this oil rig is only 5 miles offshore, and you are not going to run a tanker back and forth, right, because it's so close. So you're going to build a pipeline that will directly feed into the refinery that takes the raw oil and turns it into a diesel, gasoline, plastic, and rubber, right? So if you're making a pipeline, there is cost associated with laying those pipes. At one point in time, I did probably say that when you look at those power lines, those huge steel towers that have those really big power lines that are 100, 200 kilovolts each, one tower plus the set of wires that belongs to that tower, because you have next tower with set of towers, and then one is $100,000. So when you take a look at 10 of those, it's $1 million right there. It's expensive stuff, right? Now pipes are even worse than that, right? You gotta dig, or you have to put them underwater, then you have to weld underwater, and you have to have divers that can actually swim and stuff. So, yeah.
And weld.
And weld, yes. So that's
At the same time.
yeah.
That's too expensive. So it's like stupid expensive. It's like one of the best jobs you could ever have in terms of
Walking, what is that?
Probably because you have 6 people doing it. So we're going to have a pipe 1 mile. Let's say $500,000. I really don't know. I'm just gonna put whatever, just for the math problem. So now you're gonna look at this and you say, well, pipe underwater is twice as expensive as the pipe on the ground, so let's just run the shortest distance for underwater to the ground, and then just run the rest on the ground, which makes that straight black line, right, for the pipe to go from the oil rig to the shore, and then you run the pipe on the shore directly into the, right, so you use the shortest distances here, and let's say this is 10 miles over here. So you have 5 miles underwater, 10 miles on the ground, and you can calculate the cost as 5 miles underwater times 500,000 plus 10 miles on the ground times the 250,000 is going to give you 2.5 mil plus another 2.5 mil is $5 million to make the pipeline to go right. They're going to obviously make that up in 15 minutes, but that's okay. Now, someone else says, whoa, whoa, whoa. How about we just go the shortest distance? Because you went really around. So let's just go shortest distance. And the blue, use the Pythagorean theorem, exactly. So now we're going to have the blue cost. Because the blue cost is entirely underwater. More expensive pipe, but it should be almost half the distance, right? Let's go and check out the distance. We use Pythagorean theorem. So this distance, let's call it d, is going to be square root of what? We have 5 squared plus 10 squared is the square root of 125, which is? Yes, definitely. Is 11.2 miles. Okay. 11.2 miles. So what's the cost? The cost is 11.2 miles times everything is underwater. So $250,000. So times, that's what I said. I was just making sure that you guys are paying attention. So we'll just put half, well, let's put 0.5 million. That's easier. So times 0.5, and that's going to be 5.6 mil. All right, it's actually worse, right? So the black path wins, right? Because it is less in the cost. Fine. And now, that was just building up the suspense. And now, you get called in to see if we can reduce the cost.
My gosh.
And the first thing is you say, of course, you noobs went to extremes, right? How about we run some pipe on the ground, and then at the point when I say turn, you go and cut through. We want to optimize so that cost is minimum. Right? So now I am going to have X distance on the ground and L distance length underwater for the minimum cost. So my cost now is going to be X times 0.25 plus L times 0.5 equals the minimum. Hey, we have our objective function already, right? I am multiplying the distance x, which is the distance on the ground, with 250,000, and then I'm adding to that the cost for underwater, which is length, times 500,000, and I want that to be the minimum. All I need to do is to come up with a constraint function. It's the one that connects x to L. Sheesh. How do I do that? We are not going to use any trig. This one is not easy to see, but there is a triangle. Okay, which triangle you're talking about? X, L, and D. We can't use that triangle. X, The others? What do you mean other side x? I like the top one, exactly. This side over here. What's the length of this side?
10 minus x.
10 minus x. That is where you make your money. So do you see now that you have a Pythagorean theorem there, and as soon as you write that Pythagorean theorem, you have your constraint function. L equals square root of 5 squared plus 10 minus x squared, and now you work that out and you can plug in, you can take the derivative, solve the equation, you get your x, you get your d, you get your cost, and you collect your 30K and you go home. You go, I forgot to say, you cross the start and collect, yeah. Anyway, so what's L? L is going to be 25 plus 100 minus 20x plus x squared. L equals square root of x squared minus 20x plus 125. So now we have 0.25 x plus 0.5 times the square root of x squared minus 20x plus 125 equals minimum. All we need to do is differentiate, and that will give us the distance x. Then you can use the L equation to calculate L, and you will have the distance that you have to go on the ground and the distance for underwater to have minimum cost. So let's see. You have your derivative, that's 0.25 plus 0.5, and now this is going to be the derivative of square root is 2 times the square root with the same guts, plus the derivative of the guts goes upstairs, which is 2x minus 20. You can cancel the 2's equal to 0, right? You can cancel 2, 20, that's a 10, and then this 2. Actually, let's cancel 0.5, leave this 2 alone. And now I have to solve this equation. 0.25 plus x minus 10 divided by 2 times the square root of x squared minus 20x plus 125. That's it. You solve this, you solve the problem, because that will give you x. Well, you move 0.25 to the right hand side, becomes negative 0.25. Kill it from here. And now cross multiply. X minus 10 is equal to negative 0.5 times the square root of x squared minus 20x plus 125. And now you square both sides to kill the square root, and that will also kill the negative sign. So now when you square both sides, you get x squared minus 20x plus 100 is equal to, when you square a half, you get a quarter. So it's going to be a quarter times, and now you just have x squared minus 20x plus 125. You multiply 4 into the left side, you get 4x squared minus 80x plus 400 equals to x squared minus 20x plus 125. Move all of these to the left. 3x squared minus 60x plus 275 equals to 0. At this point, You start your browser, you type in Wolfram Alpha, and then when it pops up, you say solve, and then you just type 3x. This is applied problem. No one cares about you being able to do a quadratic equation. Plus 1. I mean, guys, if you end up on a desert island, I mean, obviously you have to do everything by hand. But approximate forms. And now we have x equals 7.11. So 7.1, or x equals 12.9 miles. Mites. Miles. Well, do we remember the problem? The whole shoreline was how long? 10. So can we have 12? No. So that's the one that goes to garbage. And we have that x is 7.1 miles. So now we can calculate L, which was what? What was L? Square root of, kill me now, 7.1 squared minus 20 times 7.1 plus 125. Get the abacus working. 7.1 squared minus 20 times 7.1 plus 125. I'll put no, I just do this. Equals approximately 5.8 miles. So now, what's your cost? Cost is x is on ground, so that's 7.1 miles times 0.25, that's 250,000, plus 5.8 miles underwater times 500,000. So 7.1 times a quarter plus 5.8 times 500,000 for a total of 4 million and then 675,000. So remember the black path was 5 million and the blue path directly through the waters for the shortest distance was 5.6, right? That one was $1 million more than this. But we're going to take 5 million, so when you subtract the difference is from the other cheaper one, the difference is $325,000, right? So what is to the company to give you as a contractor, mathematician, for this 30K? It's not even 10% of what they save. And what do they know that you did this in 15 minutes? You know what I mean? Of course, it's pretty good, right? So this is how you make money as a contractor with math, right? You get contracted by corporations to actually recheck calculations done by engineers, right? To make sure that some, $35 million operation is going to actually work.
Maybe it's just us, but all of our contractors are stupid. So,
I'm talking about
Very honest with you.
bad contractors, right? The people who do the consultants, not a contract. I mean,
How do we get into that?
well, first you have to complete your differential equations, right? So you can have this. But as a mathematician, guys, these are the types of things, right, for companies that you get to do, right? You do the data analysis as well, statistical analysis, a whole bunch of other stuff that goes into the jobs that are math-based. And as you can see, company is very comfortable, right, saving $300,000, right? They can just give you this 25 over here, right? But what is the important part here? You actually have to do this calculation, which you should be able to run in 15 minutes after you're done with Calc 1. And the most important part is to present them with a paper presentation, all right? Has words. Because these calculations make no sense to anyone. If they knew it, they wouldn't be spending 25K on you. Make sense? So your ability to write and explain in words is as important as your ability to do this calculation, which is where your project comes in. All right? When you hand in the project on the day of the final exam, and you will have, you know, three problems most likely. Those are all applied problems, something like this, right? It needs to look like a physics lecture when you open the physics book or chemistry book, which has occasional number, occasional equation, and 99% of everything else is text. Because people who have money have no knowledge of these things. That's why they hire you. And they give you peanuts, which is $25,000, right? So they can save $300,000 and have something in place that will bring in millions down the line, right? So this is the game, right? People with money know how to make money. They don't know this, right? And this is where you come in, right? So it's well worth for them to give you 25K when they don't know it's a 15-minute calculation. Obviously, you're going to put the fluff on it, and you're going to, you know, it's going to look like it's $7 million. But
take an hour.
The thing, yeah, you have your assignment. An assignment is I want you to minimize the cost. And now, that's it. You're going to come up with a proposal. But this is the part where you look around the room. You have the proposal, and you have the proposal, and you have the proposal, and you have it. Right? Everyone has the proposal over here. Sounds like Hopper. Anyway, so do you each get 25? No. When you look around, there is one winner and 25 losers. All right? That's how it works. Which is why it's very important to have that presentation in terms of writing. So if you have that sense in your head, I hate English, I hate writing, well, you have to start, you know, changing that attitude. Because your first thing is your cover letter and your resume. That is selling you to the company, right? And there's no math on that paper. And guess what? If you don't get to that part, you never get to work, right? So there's a part there. So there's no, I hate this or I hate that. They work together. You have to be able to write, and you have to be able to write well in order for your project to be chosen over everyone else's. And no one in this classroom feels threatened by anyone else. Because guess what? All of you can have A's, right? And you work together, right? And you are together in a club, and you're friends, and all of that is nice and fun. But if someone else is to walk in tomorrow in this classroom, right, with this next class, and say, I'm hiring one person from here, because I heard, you know, what you guys did in class. I just need one. Your salary will be $115K a year, and you will be running these problems constantly because I'm going to have 17 rigs, right? And we're going to keep moving them. It's $115K job. Yeah, right? Now you're going to start looking at the classroom like, who is going to be the one hired? Because only one of you will be hired.
I'll be at the bottom.
And right? So this is something that you have to consider, right? Right now, you don't have that competition. You're safe and secure here, right? Just don't go to one. But the moment you're out there, right? They receive 300 resumes, one position. They're not gonna go, these 4 are awesome, so let's just open up another 3 position to accommodate all 4. Right? That doesn't work. So we're going to work, and then the project will reflect that. So now you understand, hopefully you understand optimization. Your job is to hunt for 2 equations. And when you find those 2 equations, you will always flip the constraint to make one variable equal everything else, put that in objective to kill the variable off, take the derivative, and then solve the equation, right? So steps are always the same. Those of you who want the extra spice, took me good 45 minutes as a student to solve this thing. I don't know what your addition problem is, but when you see the Ferris wheel, right, it's amazing. An observer stands 20 meters from you can transfer into feet if you want, but 20 meters away, that's 10 times my height. An observer stands 20 meters away from the bottom of the Ferris wheel on a line that is perpendicular to face off the wheel with her eyes at the level of the bottom of the wheel. The wheel revolves at the rate pi radians per minute, and the observer line of sight with a specific seat. The Ferris wheel makes the angle theta and the horizontal. At what time during the full revolution is theta changing most rapidly? I know, right? And what is the size of the shoes that she has? That at the end. All right. So. Yeah.
The curvature of the sun as well.
Yes, and the curvature of the sun. Great. So you look at these and understand that this is your job if you are an engineer, figuring out these things, right? The metal rain gutter, right? For optimal water, right? But you also want to design replacement blood vessels and a whole bunch of different stuff that has to be optimal in pushing. The blood is not the same as water, right? It doesn't move as easy as water. The viscosity is different, right? So you have to take a lot of stuff in consideration, and you're optimizing all the time. And what you are going to do, it's always the first derivative. You know the concept, first derivative equal to 0. Can you model? Can you take what you call the real life, because this is fake life here, and transfer that into mathematical equations? Because that is what your meetings, when you get your assignments, that's what your meetings are about. I need this. That's what the company owner says. I need this. Your job is, and your team or whatever, is to make that happen, right? And mathematical modeling is the central piece of that. So we just did the word problems. You see how much, right, they can bring to the table. So I hope this made sense. We'll take about 300-second break, and then we'll talk about the exams, which are in my bag. Okay, 240 seconds break. Sure.